Hello and welcome to Mastering Quantum Mechanics Through Problems. Today's lesson is titled The Rules to Solve Any Quantum Mechanics Problem with a Three-State System Example.
Terrific!
Here's the problem setup. The question is on the following slide. This is the Hamiltonian. It's a 3x3 Hamiltonian and it's just presented to you. And this is given to you along with the normalized eigenvectors and the eigenvalues. This is eigenvector 1, ket E1 equals 1, 0, 0, and its eigenvalue is 2 E naught. This is eigenvector ket E2, 1 over root 2, 0, 1, minus 1, and it has an eigenvalue of 3 E naught. Ket E3, 1 over root 2, 0, 1, 1, with an eigenvalue of E naught. H onto ket E1 equals 2 E naught times E1, H onto ket E2 equals 3 E naught times E2, and H onto ket E3 equals E naught times E3. This is the definition of eigenvectors and eigenvalues. A, B, and C are the standard canonical basis. This is the diagonal basis. A equals 1, 0, 0, B equals 0, 1, 0, and C equals 0, 0, 1. Note that B and C are not the eigenvectors of the Hamiltonian. In general, when the Hamiltonian is off diagonal elements, for example, the minus 1 and the minus 1 here, the standard canonical basis will not be eigenvectors of the Hamiltonian.
Oh my!
In fact, if you're in state B, you're not going to stay in state B. You'll be oscillating back and forth between B and C because this subspace has off-diagonal elements. Assume that at time t equals 0, the system is prepared in a state described by the wave function psi at time 0 is equal to ket C. This is ket C. Obtain the wave function of the system psi of t at an arbitrary time t greater than or equal to 0. Part B. Obtain the probabilities of measuring the three colors as a function of time, namely probability of A as a function of time, probability of B as a function of time, and probability of C as a function of time, and verify that the sum of the probabilities adds to 1.
Steps to solve any quantum mechanics problem. Step 1. Find the eigenstates and eigenvalues of the Hamiltonian. The Hamiltonian is the key operator representing the total energy of the system. The eigenstates of the Hamiltonian correspond to the possible states of the system, each associated with a definite energy called the eigenvalue. Step 2. Express the initial state as a linear combination of eigenstates. Any quantum state can be written as a superposition of the Hamiltonian's eigenstates. This step is crucial because it allows you to describe the initial state in terms of the Hamiltonian's basis, making the problem solvable. Step 3. Multiply each eigenstate by a phase factor. To account for time evolution, multiply each eigenstate by the exponential of negative I times the energy eigenvalue times time divided by h bar. The eigenvalue represents the energy, and h bar is the reduced Planck constant. This phase factor controls how each eigenstate evolves as time passes.
AcePhysics.org. Math and Physics Tutoring with Dr. Hudis. This is question A. At t equals 0, psi of 0 is in state C, that's 0, 0, 1. Obtain the wave function of the system psi of t at any time t greater than or equal to 0. This is how we do that, and this is the procedure for any quantum mechanics problem. You may want to pause the video and try it on your own. I'm going to do it on the next slides. We're given psi of 0 is equal to C, so psi of 0 is equal to 0, 0, 1. The state must be written in terms of eigenstates of the Hamiltonian. Psi of 0 equals C is equal to 1 over root 2 E3 minus 1 over root 2 E2. You can verify this simply by taking E2 and replacing it with this ket E2 and E3 and replacing it with this ket E3, and you'll see that this linear combination of eigenstates does in fact equal to C, which is 0, 0, 1. The next step is we multiply ket E3 by the phase factor e to the minus IE3t over h bar, and we multiply ket E2 by the phase factor e to the minus IE2t over h bar. We know that E3 is equal to E naught, and E2 is equal to 3 E naught. Now we have psi of t, the wave function for any time t. If we can extract an overall phase such that these two phases have the same magnitude, that simplifies the algebra. In this case, I can factor out e to the minus I times 2 E naught t by h bar, and that leaves us with this expression, and this is going to be an easier algebraic expression. Now we have psi of t equals e to the minus 2 E naught t over h bar times 1 over root 2 times this phase factor times E3 minus this phase factor times E2. 1 over root 2 times E3 is equal to 1 half times 0, 1, 1. 1 over root 2 times E2 is equal to 1 half times 0, 1, minus 1. And then I can rewrite this in terms of sines and cosines. E to the minus E naught t over h bar is equal to cosine of E naught t over h bar minus I sine of E naught t over h bar. You then perform this simple algebra, and then you're left with psi of t is equal to an overall phase factor times 0 minus I sine of E naught t over h bar and cosine of E naught t over h bar. And this is the answer for part
Bingo!
A. Part B says obtain the probabilities of measuring the three colors as a function of time, namely, what is the probability of measuring A as a function of time, what is the probability of measuring B as a function of time, and what is the probability of measuring C as a function of time. This is for the example of psi of 0 is equal to C. If psi of 0 were equal to A, for example, the answers we're about to get would be different. This is A, B, and C, and we know psi of t is equal to this expression. What is the probability that we get B as a function of time? Well, to do that, we take bra B onto psi, and then we take the absolute value squared. You can also just look at your expression, and you can see that it's going to be the middle component squared, because this is the standard canonical basis. But bra B onto psi is equal to the middle component multiplied by an overall phase factor. The overall phase factor goes away when you square it. That's why an overall phase in quantum mechanics doesn't matter. It has no implication on the physics. And so probability of B as a function of time is equal to sine squared of E naught t over h bar. As a function of time, the probability that you measure B is going to be oscillating. It's going to be oscillating from 0 to 100%. The probability that you measure A as a function of time is 0, and you can see there's no chance that you're going to measure A as a function of time because this is psi of t as a function of time, and it's never going to be in state A. And the probability that you'll measure C as a function of time is equal to cosine squared of E naught t over h bar. So you're going to be oscillating back and forth between the states B and C as a function of time, and you'll never be in the state A.
AcePhysics.org. Math and Physics Tutoring with Dr. H. AcePhysics.org. Math and Physics Tutoring with Dr. Hudis.